Hello and welcome back to the second part of the knife-based implementation. I am Raghavendra, an expert in AI, ML and data engineering. So in this part, we shall be discussing about the implementation of the performance metrics of a classification problem. Let's start this video by taking a look at the total number of test observations which we had earlier split. That is, there are a total of 3112 test observations. I save this in object N. Here are the predictions made using the knife-based classifier along with each of the test observations. Next, I am finding out how many test observations matched with the predicted values, and I am dividing it by the total number of test observations. Here I am checking how many test observations match with the predicted values, and I am going to divide this outcome by the total number of test observations and then multiply by 100 to express it in percentage. So I get 88.43. This is nothing but the accuracy of our model on the test dataset. I can even get this using a built-in method called as accuracy_score from scikit-learn.metrics. I'm going to first import accuracy_score. Accuracy, by the way, is not the only performance metric for classification problems. So I as well import the confusion matrix, F1 score, ROC curve and AUC. To get the accuracy score, I pass the y-test and the y-pred values, which is the actual test labels and the predicted labels. I pass this to the method accuracy_score. Let's check what value we get. We get exactly the same as 88.43 which we got before. Another metric to summarize the test labels with the predicted labels is the confusion matrix. Let's now take a look at the confusion matrix. Again here we pass the y-test and y-pred arrays to the method to get the confusion matrix. So I save the confusion matrix in an object called as CM. So this is a binary class classification problem where there are two categories in the target, and hence my confusion matrix is going to be a 2 by 2 matrix. Across the rows are the actual values of class 0 and class 1, and across the columns are the predicted values for class 0 and class 1. So the principal diagonal of the confusion matrix is going to capture my total correct classifications, and my secondary diagonal is going to capture my misclassifications of the predictions. Now let's take a look at more details into the confusion matrix. So Cm of 0, 0, that is the first value of my confusion matrix, is going to give me the true negative values. There are 2690 true negative values. Cm of 0, 1 is going to give me the false positive value. Then Cm of 1, 0, that is the second row, first column, is going to give me the false negative values. And my second row, second column, that is Cm of 1, 1, is going to give me the true positive value. Accuracy can as well be computed by summing up the true negative and the true positive divided by the total number of observations. That's again, we are going to get a value of 0.88. Then there are other performance measures which we are going to see next, that is the true positive rate or the recall or the sensitivity. So let us compute that. I'm going to get that as 0.23. Specificity comes to 0.94. False positive rate, which is nothing but 1 minus specificity, is 0.054 and precision is 0.28. Now let's take a harmonic mean between precision and recall, which gives me the F1 score, that is 2 times precision into recall divided by precision plus recall, which gives me a value of 0.2561. Alternatively, F1 score can as well be computed by using the F1 underscore score method of the scikit-learn.metrics class. So for this, I pass ytest and ypred to the F1 score method, and I am going to get exactly the same answer of 0.2561. So what do we infer by this F1 score? A high value of F1 score indicate that both precision and recall values are very high. So if you are intending to have a high precision, a high recall, then your F1 score should always be high. But if either of precision or recall values are low, F1 score results in a lower value. Let's take a look at what is precision over here. Precision is 0.28, which is a lower value. Recall is as well small, which is 0.23, which results in a much lower overall value of F1 score. Let's move on further and obtain the ROC curve and the area under this curve. So here in ROC, we plot a graph between the false positive rate and the true positive rate. ROC stands for the receiver operating characteristic, which is nothing but a plot between false positive rate and the true positive rate for various threshold values. Here are the predictions which are being made by using a default threshold value of 0.5. Any probability with a value greater than or equal to 0.5 is classified as class 1, and any probability value with less than 0.5 is classified as class 0. So in most of the cases, 0.5 is used as a threshold, which need not be the right one. So what we are going to do is we are going to plot a graph by varying these threshold values, and we are going to get different true positive rates and false positive rates. So now I'm going to get the predicted probabilities by passing the X test. I am going to save it in the object props. So let me take a look at the props. So in the first row, the probability of class 0 is 9.98 into 10 to the power of minus 1, and the probability of class 1, which is the positive class, is 0.00002541, or it's nothing but 1.25 into 10 to the power of minus 3. If you consider 0.5 as the threshold, which in fact is the default one, so the probability of class 0 is higher than the probability of class 1. So for the first observation over here, the first record over here, we conclude that the prediction by looking at the probabilities will fall under class 0. So likewise, if you can observe the second row, the probability of class 0, and this is the probability of class 1. And when you look at the probability of class 0, it is much higher, and the second test observation will also be in class 0. And that's how predictions are being made based on the class probabilities. So next, I am going to extract the probabilities of the positive class, or the probabilities of class 1, which is nothing but the first column or the column at index 1. All the rows is going to be extracted, and I am going to save it in the object prob underscore positive. So then I am going to pass these values, that is ytest values, and the probabilities of the positive class values into a method called as ROC underscore curve, which is going to result in different false positive values, true positive values for different thresholds. Based on these ytest values and the probabilities of the positive class values, the ROC curve method is automatically going to generate different threshold values, and for each of these threshold values it is going to compute the false positive rate and the true positive rate values. I am going to put them all together, the threshold, the false positive rate and the true positive rate, into a data frame. Let me look at the head of the data frame for the purpose of better understanding. For a threshold of 1.95, the false positive rate is 0 and true positive rate is as well 0. For a threshold of 0.95, the false positive rate is 0.000351 and the true positive rate is 0.007491 and so on. So now I am going to get a curve between the false positive rate and the true positive rate. I am going to as well compute the area under this curve, that is going to come to around 0.8463. Next, let's plot this curve between the false positive rate and the true positive rate using matplotlib. So I am going to plot that over here, and this is the code for getting the plot. I am going to use matplotlib.pyplot and then get a graph between my receiver operating characteristics, that is my false positive rate along the x-axis and the true positive rate along the y-axis. For different threshold values, our false positive rate and the true positive rate changes, and for a particular threshold value, true positive rate reaches a maximum. It almost goes on till 1.0, and so is your false positive rate. So the area under the curve of this graph between the false positive rate and the true positive rate is a measure of how better is your model going to perform for a different threshold values. So the maximum the AUC, better is your model in making correct predictions. So here is the result of the area under this curve of the receiver operating characteristic. That is, the false positive rate versus the true positive rate is 0.85. So in this video, we have implemented the different performance metric of a classification problem, and we have understood the different performance metrics as well. Thanks for watching this video.